Well, the topic of the presentation is centralized WAMPACs, which means wide area monitoring, protection, automation, and control systems. And it's the architectures and the applications and the benefits of this technology. The topic is important because the electric power industry has changed. Today, instead of having just synchronous generators, we have a lot of distributed energy resources that are renewable, and because of that have variable characteristics. And in order to control the system under these conditions, we need to be operating in a situational awareness based on this kind of system. People have to start thinking about the process interface devices that can provide this kind of information. And once we have the information, we have to find the most efficient ways to deliver the information to a central location or a hierarchical system in order to process it in the most efficient way. One of the buzzwords that we like to use is smart grid or smarter grid or something like that. And actually, this is the conceptual model of the smart grid that you see on the screen. And you see that it has many different components. And what I like to do is I like to split them in two parts. One is the physical layer that we can call it, and the other is the operational layer. So when I started my career, we had bulk generation, we had transmission, we had distribution, and we had customers. And everything was very simple because you bring from a power station the power to the load center. You go to the distribution level where you have radial feeders. And on these radial feeders, you have non-directional overcurrent protection. And then you go to the customers that were pretty much fairly straightforward, mostly heating, light bulbs, and maybe some washing machines, refrigerators, maybe a stove or something like that. So very, very simple loads. And if you lose power for maybe 5 minutes or 10 minutes or 15 minutes, it was not a big deal, because what maybe you will be watching, especially I grew up in a communist country, so we didn't have television, but even if you had television, you don't want to watch it because it was just propaganda. So it's not a big deal. And because of that, everything was really simple from the point of view of the protection and control. Then, when I moved to the US, what was different is that the customers were more sensitive to the interruptions because the characteristics of the load have changed, and we were starting to talk about power quality. So power quality was one of the driving forces on top of the stability of the electric power system. But still, we knew how the system behaves because all these bulk generators were synchronous machines, and we knew how to model the synchronous machines. We knew how to do dynamic stability studies. We knew how to determine what is the fault clearing time that is critical for the stability of the electric power system. And the distribution system was still radial, so the protection was also still simple. But what we have today is something that is a completely different electric power grid. I think when we had the PacWorld conference in Glasgow in June this year, somebody told me that there were a couple of days when at least part of the UK was supplied exclusively by renewable generation. And when we have renewable generation, there are certain issues that we need to think about. Because, again, the answer is it depends. It depends on what type of renewable generation do we have. For example, if you ask Ranveig about renewable generation, she will say it's not a problem because we have all these hydro power plants that we can properly manage because they are connected to a dam with as much water as we need to run the electric power grid in the most efficient way. However, if this renewable generation is a solar power plant like you have, for example, in China, I don't know if you know what is the largest solar power plant in the world, and it's in China. Do you know what is the output of this power plant? 1.5 gigawatts. Now imagine the surface that this power plant takes, and imagine that you have a cloud system going over this power plant. The generation is going to be continuously changing because of the impact of the cloud coverage of this area of the power plant. If you have wind generation and you have a big wind farm that is covering a vast area, the speed of the wind is not going to be the same. Maybe not all the wind turbines will be operating at every moment in time. So it is a variable characteristic of the generation. And from the point of view of the control of the electric power grid, when you have to deal with variable generation, things become quite challenging. You cannot just do it based on some assumed schedule from the day before based on the load forecasting. You have to have awareness of what is the available generation at every single moment in time. And this is why we need to do the protection, automation, and control in a very different way. And this is where actually the problem is. So I think it becomes clear what kind of a problem that we have, and also I can mention the fact that many of these renewable generators are not synchronous machines. They're connected with inverters to the grid, which means that when a fault occurs, we don't have fault current because the inverter maybe will have a spike for a couple of milliseconds, and then it will say, no, I'm not going to contribute fault current to the system. I'm going to just take some measures to avoid damaging equipment. But this is where things become really funny, because I remember when I was in university and I was studying about protection, they were telling us that the protection is there to try to clear a fault condition that is causing a lot of fault current and low voltages to go through the equipment, so we have to prevent damaging this equipment. So this is how we designed the protection systems, to work with these high currents and low voltages. Today, some people in the protection industry complain that we don't have enough fault current. And there are some crazy people that say we have to program the inverter controllers to produce fault current, which I find absolutely ridiculous. We have to find new methods for detecting the faults and then taking care of the abnormal condition in order to maintain the stability of the electric power grid and the power quality that we provide to our customers. And then the last very significant change is the fact that today we don't have just a consumer anymore. I was going to say I live in California, but actually that will not be a true statement. I have an address in California. But in California, you can see everywhere solar panels on the rooftops because we get a lot of sun. So as a result of that, the customer, the consumer, is not just a consumer anymore. And this is true not only for California. There are many places around Europe that don't have that much sun, but even because they still have some time sun, they install a lot of solar panels on their rooftops. So actually these people, they become what we call a prosumer today, because at a certain time when the sun is shining, they may be producing much more power than they need, and they are exporting this power, they're delivering it to the grid in order to support the balance between the load and the generation. So this is something that now completely changes the requirements for the protection and control of the distribution grid, because we may be having power flows in the reverse direction, or we may be having an energized line after the line is stripped from the substation. So this is a significant change as well. Now, when we start thinking about the control of the electric power system, this also changes. So I go into a little bit detail here at the distribution level, because I want to highlight a couple more things. First of all, you have all the distributed generators, but on top of that, you have two other different types of resources. One of them is the batteries, which are stationary batteries that can be at your house, or they can be grid-level battery storage that is used to balance the load at certain moments in time. But also you have the more challenging issue of mobile batteries, which is the case of the car, because you can consider the car from the point of view of the electric power grid as a mobile battery that you don't know at which moment in time where it's going to be. So this also requires actually for us to support the ability to gain awareness of where are all these storage devices and what is their operating mode, because this will have an impact on the control strategy that we are going to implement. So for example, if we have a lack of power, we are going to use these batteries to provide power to the grid. So if they are in a charging mode, we are going to switch them from the charging mode to a generating mode in order to meet the requirements of the electric power system. But this requires actually a different approach than the conventional, because the conventional system operator was basing their decision knowing the amount of generation and spinning reserve that is available from a power station at the bulk level of the system. Today, imagine if the system operator has to get data from all the individual solar panels or car batteries that are available in the area that they have to control. This becomes an impossible task. This is why what we are doing within IEC 61850 in Working Group 17 is we are working on the modeling of the distributed generation, the distributed energy resources. We are talking about hierarchical control structures. We are talking about DERMS, the distributed energy resources management systems, etc., etc. So I think it becomes clear that what I'm doing in the whatever 10, 15 minutes since I started talking about this topic is I'm trying to answer the question of why do we need wide area monitoring, protection, automation, and control systems. And I think to summarize the answer is, as I said at the beginning, is because it's a different grid. And the only way that we can deal with it is by using this kind of systems. Now, the next question, you remember, is how are we doing it? And I think the answer is clear, it depends. Now, you should be very careful with the "it depends" answer, because "it depends" is just the start of the answer. So if, for example, you go to your boss and he asks you a question and you just answer "it depends" and you walk out the door, you may be in deep trouble. "It depends" is just the starting point that gives you a few seconds to think about what does it depend on. And this is what I'm trying to answer here. It depends on what? And there are many, many different factors that have an impact on our answer. For example, what is the use case? What are we trying to do with this wide area monitoring, protection, automation, and control system? Is our main focus monitoring? Is it protection? Is it automation? Is it control? Is it a combination of all these? And I will try to give you some examples to highlight actually how all these things are interrelated to each other. Because you cannot do protection today without monitoring the system. You cannot do protection without thinking about the automation that follows the clearing of the fault. So all these issues are interrelated, and this is what makes our life so exciting. At least it's exciting to me, but I assume that since you're here in this room, it's exciting to you as well, because if you didn't care, you won't be here. You will be sitting in front of a TV, watching a stupid reality show, and wasting your life, okay? But we are trying to do something here to change the world, okay? So the next question may be, what is the area? Because when we say wide area, how wide is the area? Is it maybe this neighborhood? Is it London? Is it the county where London is? Is it England? Is it the UK? Is it Europe? Is it the world? Is it the universe? It depends on how big the area that we are covering is. And actually what you're going to see is that this has not only logical impact, but it also has physical impact. Because when we talk about wide area monitoring, protection, automation, and control systems, they are impossible without communications. But the communications, even if you have the highest speed technology available, the latency of communications depends on the distance, because we have physics limitations that limit the speed of communications based on the distance between the 2 points between you, which you have to communicate. Another question is how critical it is, because depending on the criticality, it will have an impact on the design of your system, on the redundancy, on the communications architecture, on the cybersecurity approach that you can take, etc., etc. What are the performance requirements? If we are to clear a fault, how fast do we need to clear the fault? What is the criteria? Is it maybe a write-through characteristic? Is it a dynamic stability requirement? So we need to have a good understanding of what are the performance requirements. Another one is how much money we have, because depending on the money that you have, you can build a different design that will meet in a better way maybe the requirements that you have imposed. So, and obviously, another very critical factor, since we are at the IC 61850 Global Conference, is how familiar you are with IC 61850, because I really believe that IC 61850 is the tool that we have available to us to design and implement wide area protection, automation, and control systems. So, since I'm the editor-in-chief of PacWorld, the first thing that I will suggest, because I can talk on this topic for hours, and I have only 35 minutes, and I have only maybe 13 minutes left. So I would suggest read the September issue of the magazine, because it is concentrated on wide area protection, automation, and control systems, and there are 5 very interesting articles that can give you some ideas about what people are doing in this field, and a lot of it is based on IC 61850. Now I have to speed up, because I have maybe about 60 slides for 13 minutes. So I'm going to skip a lot of them. I'm going to just highlight some of the most important ones, and then you're going to get a copy of my presentation, and you may be looking through my slides and thinking, what the hell was he thinking about talking on this slide? But anyway. So this is a very simplified block diagram of a utility automation system, and the reason I put it is because you can see that in the middle of it is the different IEDs that provide us the interface with the physical layer of the grid. This is where actually the sensors are, this is where the measurements are, this is where the local automated and protection decisions are made. But once we get outside of the process level, we go to the network control center, we may go to a human operator, we may have some primary equipment that we have to automate or operate on, and then we have the communications, and then the communications bring us to teleprotection or any other related functionality. So this is a very, very simplified view of the utility automation system. A lot to do with the wide area monitoring, protection, and control was done within Working Group 10 on a report, on a technical report called 19-5 that I'm going to spend a little bit more time on. But one of the things in this report is a bunch of use cases with their requirements for the reporting range, end-to-end latency, measurement, timing error, etc., etc. So this is something that I recommend for you to study. But I'm sure that you probably have in your company something similar that defines what are the applications and then the specific technical requirements for their performance. Just to give you a few examples of the functionality of this kind of systems, this is an example of oscillation detection based on synchrophasor measurements. This is another example of WASA. WASA, I'm not having time to challenge you to figure out what it means. It is a wide area situational awareness system. And the reason that we have this kind of situational awareness systems is to help the system operator. Because I don't know if you know, but I can tell you after a significant research that I did is that the humans have not been designed to process numbers. We are much better in processing analog information. And this is why I know that, for example, for pilots and for many other operators of different equipment, the reaction time of the human being is much better on analog information that is graphical than processing a value of the number, because then you have to think about the threshold, you have to think about how far you are from the threshold and things like that, and this slows down the processing time of the human being. And this is why the wide area situational awareness systems are designed to provide this digital information coming from the PMUs in such a way that it will support the operator in his faster estimation of the state of the electric power system. But the most critical wide area application is what we call the system integrity protection scheme. So I have a bunch of slides on the SIP's functionality. It's an exchange of information in order to determine if it's a critical state of the grid. And then based on this, we have to make a decision of what kind of action we have to take to maintain the stability. There are different elements that are used to build this kind of a system. So we have mostly system monitoring elements, protection elements, and execution elements. And just to give you an example, the monitoring elements are used to detect a change in the power system, detect a change in the load, and detect the change in the generation, and then based on all these changes to make a decision of the criticality of the state of the grid and what kind of action needs to be taken to maintain it. Now, what you see here is I put this slide together because the topic is centralized WAMPACs. And when we are using a term, it's always a good idea to ask the question, what do we mean by that? So when we say centralized system, what do we mean by that? In the very pure form, the way I will define it is a system that has a bottom layer of process interface devices that are interfacing with the analog sensors, the status information, etc. And then I have a global centralized device that is going to get all this data and then process the data, make a decision of what has to happen, and send the control signals to the process interface. But if we are to do that, imagine the amount of data and the processing time and the latency that is going to affect the overall efficiency of the performance of such a system. And this is why, to me, the best solution is what I call a hybrid system. That is an hierarchical system that is designed in such a way that it will take the fastest action possible as close as possible to the problem area. So I can have a local SIPS in the substation. I can have a regional SIPS in a regional control center. And then I can have the global SIPS. And all these systems, they have to have horizontal communications between themselves to help them understand the overall state of the system. And then they also have coordination in a vertical communication interface in order to get the top view of the system that will support the local decision. Once we decide on the hierarchy and once we decide which kind of system we will be implementing at which stage of our project, we need to look into the components. So this is an example of the system monitoring component. This is an example of the process control that controls actually the breakers. And this is how we model all of this in IEC 61850. So what you see here is that we have the current and voltage sensors that are providing sampled values to MMXUs. The MMXUs are calculating local phasors or synchrophasors when we have the communication and the process and the time synchronization interface. And then we also know the state of the system based on the system model, knowing the line impedances, et cetera, in order to make the best decision for our specific application. I'm not going to spend a lot of time on synchrophasors. I think synchrophasors now are available in pretty much all multifunctional protection and control devices. And they have been around for quite some time. Actually, when I was working for New York State Electric and Gas at the beginning of my career in the US, actually we had one of the first PMUs in the world. This was in 1993. So before even 1344 was published as a standard. So we were doing a lot of crazy things. We had an optical CT, we had a 6-phase line, so we've done any crazy thing that somebody can think of. We just didn't have 61850, unfortunately. But that's why we came up with the idea. So this is the whole idea. You have GPS synchronized devices that are using time as a common reference to see the relationship of the phasors at different points in the electric power system, and they can be used for many different applications that I was briefly mentioning. This kind of communications is defined in the IEEE 37118 standard that defines actually the time reference as UTC, the total vector error, the rate of the measurements, etc. And actually, one thing that is interesting is that it is based on a cosine function, meaning that actually the value of 0 degrees is not at the zero crossing, but it is at the maximum of the positive sine waveform. So this is something that you should keep in mind when you test, because normally the test equipment uses the zero crossing as the reference. So you think that you are applying a 0 degree voltage, for example, and the PMU will say minus 90. And you will say there is something wrong here. Well, wrong is the reference point from the method for calculation. Why did they pick the top of the positive waveform? Don't ask me. Ask Arun Fatke and Mark Adamiak, okay? So anyway, it also defines communications and the date format. This was replaced later with the 118 edition 2 standard, if I can say, that was split in 2 parts. Part 1 defines the measurement of the synchrophasors, and part 2 defines the communications. What is important to understand is that the definition of the calculations introduces 2 types of synchrophasors, 2 classes, the M class and the P class. The M class is for monitoring of slow changes in the system, and the P class is for the high-speed changes and protection applications. So when you're designing your WAMPACs, you have to be very careful which of the synchrophasor classes you're going to select. So this is a few slides about 37.118.1 and 2. And the next thing we need to understand is that, as I mentioned, it doesn't make sense to send the individual synchrophasor measurements from every PMU all the way to the central or regional center. What we do is we use the concept of a PDC, a phasor data concentrator that collects the data from several PMUs and sends a single stream of data. And the hierarchy of this can be quite complex. So you see here we have local PDC and regional PDC, and then a PDC for the SIPs or for the control center, etc., etc. Just to give you some examples, this is not a fantasy. A lot of utilities are implementing this kind of system. So you see the remedial action scheme. That's what Hydro-Quebec calls it. Or what you see here is the CRAS, the centralized remedial action scheme that Southern Cal Edison has implemented. And I'm more or less at the middle of my presentation, but I ran out of time, so I'm going to stop here. And we have 5 minutes for questions.